Hi 253. In this video we're going to continue working with infinite series, but now we're going to use them to approximate functions. And we're going to approximate functions that are not polynomials, so technically things like logarithms and exponentials and trig functions. So the first thing I want us to consider is a new kind of series. So far our series have been series that make use of adding up a bunch of real numbers. But now what I'd like to do is consider a series where we're going to be adding up terms that contain a variable. So these are called specifically a power series, and these are series of the following form. They are infinite series here, but each of the terms contains some power of x, and we'd like them to increase by 1 as we move out into the throughout the sum, throughout the series specifically since it's infinite. Each of these is going to have some kind of constant living in front of a power of x. We're going to start out with a 0 power on x here in the first term so that we get a constant term. Then we're going to add a first power of x with a constant, second power of x with a constant, and so on all the way out, right? Notice here that this is different than what we've been considering before, because all of our series before have only had a term described by just a formula to give you a real number, right? Now we're going to say that our terms contain some kind of variable. Alternatively, what we can do is consider this in a more general form. The second one is just a restatement of the first one, and you've probably, actually, we've talked about it in class, this idea of replacing x with x minus a. If you're remembering back to 111, this had something to do with some kind of horizontal transformation, right, a shift left or right, and this will make more sense, and that'll have an actual application later when we consider these things like polynomials. But for right now, this is just a more general form of what we have restated here, because notice if I let a be 0, if I let a equal 0, I get the form above, right? In general, we say this one is maybe better to use sometimes because it's more more general, I guess. But we say that a, this little a that's right here being subtracted away from x, this is the center of the series, right? And so instead of our terms looking like this, where we would say the center is 0, right? Because we let a be 0, the center would be 0 here. Instead, we have our polynomial, which looks something like this, where in each of the terms we have an x minus a expression, right, being raised to some kind of a power with a constant out front, of course. Okay? So why would we even want to consider a series like this? What are they useful for? So we can use these power series to approximate behaviors of functions, quite honestly, because we're going to be considering these things as technically infinite polynomials, right? This is just an infinite polynomial on the right side right here, right? And that's its summation notation for it, right? So taking these infinite polynomials here, we're going to be able to use these things in very special ways by applying specific values for these c's right here. See these values of the coefficients right here? We're going to be able to use specific numbers right here in front of these powers of x so that these power series, these infinite polynomials, can be used to approximate other functions. The functions we're going to be approximating are functions like logarithms, exponentials, trig functions like sine and cosine, and perhaps tangent if we like. And the reason we might want to do that is because functions like logarithms and exponentials and trig functions are not easy to evaluate for any value of x. For example, if you wanted to evaluate sine, if you wanted to plug in 0.5 into sine, it's kind of tricky. You don't know what the value of sine is at 0.5 directly off the top of your head, right? If we were able to approximate the sine function using a polynomial, perhaps, these polynomials are easier to evaluate for a certain value of x than sine would be, right? Because notice that these polynomials here just make use of the basic 4 operations: addition, subtraction, multiplication, and division. Division if your values of the coefficients have a fraction in them or something like that. But these basic operations really turn evaluating sine at 0.5 into using arithmetic, technically, if you were going to approximate sine using an infinite polynomial. So really the idea is taking yucky functions, approximating them with an infinite polynomial, and using those infinite polynomials to approximate the value of the function, right? Just so that we can turn it into basic 4 operations, right? These 4 operations found in polynomials. Okay, so we're going to have to do good approximations though, right? We don't want to use bad approximations, so we're going to have to figure out ways to make these good approximations. So to start out this idea of approximations, I want us to recall from 251 the idea of a linear approximation. These are okay approximations. Remember, the idea with linear approximations is that you are approximating a function like f of x here at a point, right? So say we wanted to approximate the function f with its tangent line, right? That's technically what a linear approximation is. This is the tangent line to the function f at a. If we want to approximate the function f at a using its tangent line or linear approximation, what that means is that we want to write the equation of the line here, right, for which the line is agreeing at this point and agrees with the slope of the function at that point as well, right? So we could, instead of calling this y equals f of a plus f prime of a times x minus a, which is the linear approximation, right? Instead of calling it y equals, we could call it a polynomial, for example, p1 of x, right? And you'll see why we use that later. But we could call this a polynomial. It would be a first degree polynomial because we have a first degree polynomial on the right side. Highest power of x is 1, yes? A couple things to notice here are that because we're writing a tangent line, right, the line and the function agree at both value and shape, right? What that means here is that if I were to say what is p1 of a, if I plug in a into the linear approximation here, into the equation of the tangent line, what do I get? When I plug in a, that means this part over here is going to be a, right, which means this whole thing is gone, so I just get f of a. Okay, so what that means is that the tangent line or the linear approximation agrees with the function in terms of value, right? Their value is the same. Okay. Instead, down here, if we say what is p1 prime at a, that means first take the derivative of p1. What is the derivative of p1? The derivative of p1 is the thing in front of x, right? The thing in front of x, which is this, yes? Okay. And then, of course, evaluate it at a. Well, that would mean plug in a into here. Well, that's just a constant, right? The reason it's a constant is because it's a line, right? And its slope is always the same. So what this means right here is that the line and the function agree in terms of shape or direction, right? Their direction is the same at a, right? They are both headed in sort of this upwards to the right direction at a. Okay, so they agree in both value and they agree in both shape, or actually, which would even be better to say, direction, right? Because technically, they don't really agree in terms of shape, do they? We're saying that this curvy thing looks the same. Does it quite look the same as the line? No, it just looks sort of approximately like it at a specifically. But notice our function has like curviness to it, right? It has what's called curvature. The line does not have any, right? And so what that means is that our line is not really well approximating the function as you get farther away from a, right? If you move anywhere away from a, the line no longer well approximates the function, right? So for example, if you were looking over here at whatever this value of x is here, yes, the line does not give you a good approximation for the value of the function there. The line would say that it's approximately whatever this y value is, right? Yes? But the function actually says, nope, I'm way up here, right? So anywhere away from a, this tangent line here is not giving you a good approximation for the function, right? And that's technically because the line has no curvature, right? And the function does, right? Well, how can we improve this? Because this is not good enough, right? This is not good. We could do more than just approximate our function by a line. Perhaps we could approximate it by something that does have curvature. What is the first non-linear graph that you know of? Well, the first thing that you know of that's not a line when we graph it is a parabola, yes? Would it be possible for us to approximate the graph of f at a with a parabola? Well, sure. What would it have to agree on? It would have to pass through this point here. It would have to pass through that point. It should agree in terms of slope, right? So it should still be heading in the same direction. But also we'd like it to agree in terms of curvature. The concavity should agree, yes? So if we were to approximate it with a parabola, we would want it to maybe do something like that, yes? Okay, we would like both the value and the direction and the concavity to be the same, right? We want it to have like the same kind of bold up shape there at that point, right? So let's see if we can get the concavity to match, right? Let's approximate using a quadratic. We're going to approximate the function f at a using a quadratic. We're going to call this a polynomial because a quadratic is a polynomial. It's going to be a degree 2. Why? Because we want to use a quadratic. We want to use a parabola, right? Okay, so first things first, we know that at the very least we want them to agree in terms of value, right? Right here, this right here is necessary because we want P2 at A to equal f of A. right? And isn't that true? If you plug in a for x, all the other stuff back here is going to disappear, which means they agree in terms of value, right? So the value is the same still. We want them to pass through the same point. Well, what about P2 prime at A? Well, what would that be? Well, if P2, we want to look at P2 prime first of all. So what would the derivative be? What would the derivative of P2 be? This would be gone. F of A would be gone. The derivative would keep this term here. So we would have F prime at A for here. And then we would have some stuff over here, right? We would have 2c times x minus a. But wait, we're going to plug in a, aren't we? So when we had over here the 2c times x minus a, all this stuff is going to be gone because you're going to plug in a in a second and all this is going to be gone. So what does this say? P2 prime at a equals f prime at a, which means what? It agrees in terms of direction still, right? The direction will be equal. Excellent. So the last thing that we want to have happen is we want the concavity to match, right? So we want the following to happen. We want P2 double prime at A to equal what? The concavity of F at A. Yes? Because that way their shape will match, their concavity will match. Well, what is the second derivative at A going to look like? Well, if we think about the second derivative of this thing, the first derivative, remember, had what? F prime of A plus, and we would have this part first before we plugged in the a, right? We would have plus 2cx minus a, right? Okay, so P2 double prime at a, P2 double prime at a, okay? P2 double prime, first of all, would be, this part would go to 0, right? This first term would be 0. We would have what? 2c, right? Because it would have this right here. Okay, because it would be the stuff in front of the x right here. Then you would evaluate it at a. There's nothing to plug in, so it's just 2c. We want this to equal f double prime at a. Okay, so the question is, the reason we put this whole part here in at the end, right, is because we wanted it to be quadratic, but we didn't know what to put here, right? We don't know what to put here so that P2 agrees in terms of concavity with f. I think we were just able to find out what C should be so that it does agree, because notice that we want this to equal F double prime at A, right? That's the set it equals to equal, right? So what this is telling us is that C should be what? C should equal 1/2 F double prime at A. If that's what C equals, then we know that P2 double prime at A, the second derivative of P2 at A, will equal the second derivative of F at A. The concavity will equal, right? So what that means is that for our function f to approximate f at a, we should use the following quadratic. We should use f of a plus f prime of a x minus a plus 1/2 f double prime at a times the squared part, right? X minus a squared. Okay, using that quadratic will give us a parabola which agrees in both value, direction, and concavity, right? So we will have both the value the same, the direction will be the same, and notice the concavity. The concavity is really nice right there. It matches exactly, right? To see this more specifically, let's consider one of our animations from our textbook. Here. So this is one of the animations from our textbook, and we're approximating a function f using a tangent line as well as a quadratic. Notice I've checked the linear and quadratic boxes here. Let's see what happens as we move a, right? As we move the value of x that we're approximating our function at, right? You'll see that the line and the parabola both change shape. Why is that? Because we're wanting to have both the value, the direction, and the concavity agree, right? Notice that the parabola that we have always sort of mimics what's going on at that location of a, right? The parabola wants to look just like the function. Either it opens wider because at that point it's a nice wide shape, or it becomes narrower because the concavity increases, right? It's more concave sort of down here, so the parabola has to be sort of skinnier to accommodate for that, right? And it opens back up as the curve gets less concave, right? Less concavity. Okay?